Hello, in this video we're going to look at some properties of rings. So here we're going to talk about some basic facts, all involving a ring and elements. So let R be a ring, and let A and B be elements in the ring. Then you've got the following facts. This is true for any ring whatsoever. The first fact is that multiplication by 0 always gives you the 0 element back. Remember here, 0 is the additive identity. So this familiar property from matrix multiplication and from multiplication of real numbers is true in complete generality. And here's the reason why, or at least one proof why. Suppose you add 0a plus 0a. Well, by the distributive property, you can factor out the a, and you have 0 plus 0 times a. But 0 is the additive identity, so 0 plus 0 is just 0. So now you have 0a plus 0a is equal to 0a. On the other hand, you can add another additive identity because 0 plus 0a is equal to 0a. And so what you've managed to show is this equality. So by cancellation, you can cancel out a 0a, and you have 0a equals 0. Note that it follows from this fact that division by 0, well, for one comment, the proof of the other cancellation law, multiplication rule, is similar. You just put the zeros on the right instead and use right distributivity. The other remark I wanted to notice is that this is why division by 0 doesn't make sense. Because suppose it made sense to talk about division by 0. So, a divided by 0 was equal to something called x. Well, then what should a divided by 0 times 0 be? Well, rules of cancellation says you should get a. But according to the property we just proved, you must get 0. So this tells you that a has to be equal to 0. So it tells you a divided by 0 is undefined when a is not 0. So in order to be a ring, for multiplication and addition to satisfy all the properties we want, division by 0 just doesn't make sense. The only way around it would be that you would have to get rid of your favorite property, which is that where you would allow this cancellation. But as you'll see later when we discuss fields, that's not really a good idea because, that's the whole reason we discuss fractions in the first place. And the whole reason we invented fractions is for the cancellation property, which is guaranteed to work and can be proven when b is non-zero. So we discover that you can't get things to work when the denominator is 0, and so it turns out you just don't have a ring in that case. That being said, let's move on to our next fact. It says that if you multiply the negative of a times b, you actually get the additive inverse of ab. Which is the same thing happens if you multiply a by the additive inverse of b. Why should this be true? Well, what is the additive inverse of ab? It's a number with the property that when you add it to ab, you should get 0. So to prove this, what we're going to show is that if you add negative a times b to ab, you get 0. How do you do that? Well, there's a common factor of b here that you can factor out. A plus negative a is equal to 0, and as we just observed, 0 times b is 0. So we have that the additive inverse of ab is negative a times b. A similar proof works on the other side. Just now you do a negative b plus ab, and you factor out the common factor of a. Finally, our third fact is that negative times negative is positive. Here's the algebraic proof of that fact. It's just using fact 2 twice. First, you bring out the negative from the a. That's this equal sign. Then you bring out the negative from the b, that's the second equal sign. And then you use the fact we've proven before in groups that if you take the double inverse, you get the original thing back. So a double negative is a positive. So note, this is true in any ring. In any ring, if you multiply two negatives, you get a positive. Even for complex numbers, matrices, anything like that. So those were basic properties. For the rest of the video, I'm going to talk about other properties a ring might have, and that in those cases, which axioms you still need to check. So here's the thing about commutativity. Suppose you've got multiplication and addition. Suppose multiplication is commutative. Then the left distributive law holds if and only if the right distributive law holds. In other words, when you're trying to prove R is a commutative ring, you only need to prove one of the distributive laws. You don't have to prove both. But if R is not a commutative, the multiplication is not commutative, you will have to prove both. So here's the proof of that fact. Suppose you've got three elements in your ring, and we're going to assume A times B plus C is equal to AB plus AC. So it's not a ring yet, it's just a set, and we're just assuming this property holds. Well, now let's look at what happens when I compute B plus C times A. By commutativity, I can move the A to the other side. Now I can distribute because I'm assuming left distributivity. And now I can commute each factor. And voila, I see that this is exactly what happens if I were to distribute the A. So I see that if I assume left distributivity and commutativity of multiplication, I can prove the right distributive law. Similarly, if I assume the right distributive law, and I start with A times B plus C, I can move the A over, distribute, and then commute each factor separately, and I get the left distributive law. So the two are equivalent when you have multiplication is commutative. So if you have a commutative multiplication, you only need to prove one of them. Another condition a ring might have is it might have something called a unity. A unity is known as a multiplicative identity. So an identity with respect to the multiplication instead of the addition. And it's almost always denoted as 1. And so another fact you can use is if R is a group under addition, and you have both distributive laws, and there's a unity, then R is actually an abelian group under addition. In particular, this means that R is a ring with a unit. So the only thing I'm skipping here is I'm not assuming that you have commutativity under addition. I'm concluding that you get it. And so here's the proof. What do I need to prove? I need to prove for any two elements A plus B equals B plus A. That's the only axiom for an abelian group I am missing. Here's the clever way we're going to prove it. I'm going to multiply A plus B times 1 plus 1, and I'm going to compute it two ways. First, we distribute this direction. So I got 1 times A plus B plus 1 times A plus B. Now I distribute the ones themselves to get A plus B plus A plus B. On the other hand, an alternative approach that's equally valid would have been to distribute the 1 plus 1 terms first. To get 1 plus 1 times A plus 1 plus 1 times B, and then to distribute the A term and the B term. And that gives me A plus B plus B. So these two expressions are the same, and so these two expressions have to be equal. So I get A plus B plus A plus B is equal to A plus B plus B. I'm working with an additive group, so I can cancel out the A on the left. I can cancel out the B on the right. And so I can conclude that b plus a is in fact equal to a plus b. The point behind those last two results is that if you ever have to check or prove something is a commutative ring, all you really need to do is look at all the ring axioms, throw away one of the distributive law ones, and replace it with the commutativity for multiplication. Check. So even though this looks like it's more conditions, it's actually the same number, which is a useful fact because actually showing commutativity for multiplication takes less writing than a distributive law. Similarly, if you want to check that if R is a ring with unity, then you look at all the ring axioms, you delete the commutativity for addition one, and you replace it with the unity axiom, which is just saying that 1 times a is equal to a, is equal to a times 1. Notice, of course, unlike the case of groups, you actually do have to check multiplication on both sides. But again, usually this proof is easier than commutativity, so it's less work. And of course, if you want to check that R is a commutative ring with unity, you can even get rid of one of those. Get rid of that, and now you're just checking commutativity from multiplication and one of these unit axioms. Of course, if all that's confusing, nothing stops you from going through the extra effort and doing all the hard work anyways, but nothing stops you from skipping the step and just quoting the result and saying you know that it has to be right distributive anyways.